Let's talk about conditional probability. Pretty simple concept. It's basically the probability of something occurring given that something else occurred first that it depends on. Good real world example is if you go to Amazon.com and look at the feature that's like people who bought this also bought, or people who viewed this also viewed. You can think of that in terms of conditional probability. What are the odds of purchasing another item given that you purchased this other item first? Same concept. Now the notation in conditional probability is probably the most confusing part. So we're going to try to walk you through it in this lecture, but it would help if you grabbed an extra cup of coffee or put on your thinking cap, whatever it takes to get yourself into your sharpest mental state, because this is one of the more challenging things to get through. With that, let's dive in, and I'll try to make it as simple as possible. Let's talk about conditional probability. Again, simple concept, but the notation can trip you up sometimes. So let's just dive into what that notation is and what it means. Now, the basic concept of conditional probability is that if I have two events that depend on each other, I can make a statement about the probability of that second event occurring given that the first event occurred. Now, the notation that we're going to use here is twofold. There's PA comma B, and that means the probability of both A and B occurring independently of each other. And then we have P of B bar A, that's the probability of B given that A has occurred. So that implies some dependency between B and A. And we can tie this all together using this handy-dandy equation here, where the probability of B given A, that is the conditional probability of B given event A, is equal to the probability of A and B together divided by the probability of A. So you can use that to tease out the conditional, the dependence between B and A. It'll make more sense with a real example, so let's take a look at a real example. Let's say that I give my students two tests, and overall 60% of my students passed both tests. So if we call the tests A and B, PA comma B would be 60%. However, the first test was easier. 80% of my students passed that one. So if B is the second test and A is the first test, P of A would be 80% in this example, right? You can see this gets confusing pretty quickly with all the A's and B's and commas and pipes, but let's review again. So 60% of the students passed both tests, so P of A comma B is 60%. The first test was easier, 80% passed that test, so P of A is 80%. So now how do I figure out the percentage of students who passed the first test who also passed the second? So what's the probability of passing my second test given that you passed the first test? That's conditional probability. So we're asking for the probability of B bar A, the conditional probability of passing test 2, given that you passed test 1. And we can compute that using the equation that we just saw. P of B bar A, the conditional probability of B given A, is equal to the non-conditional probability, PA comma B, which was 60%, over the probability of A, which is 80%. And if we do that division, we end up with 75%, and we can say that 75% is the conditional probability of passing the second test, given that you passed the first one. Make sense? Hit pause and digest this for a minute, because with all these letters and different punctuation marks and whatnot, it can get confusing. So let me just dive you into a notebook and we'll go through a bunch of other examples to try to make this notation and how to handle all these things second nature to you. And when we're done, I'll give you a little bit of an exercise so you can go and practice it yourself. So go ahead and open up the conditional probability exercise IPython notebook file and you can follow along with me here. And we'll go through some more examples of using conditional probability in different ways. So what I'm going to do is create a fake data set here that generates 100,000 random people, and it's going to segment them evenly into different age groups, 20-year-olds, 30-year-olds, 40-year-olds, 50-year-olds, 60-year-olds, and 70-year-olds. And I will also generate a number of purchases that each individual has made. And I'm going to create a dependence between the age group and the number of purchases they make. So that's what this code is doing. It's basically generating 100,000 random people, randomly choosing from a decade that they might belong to in terms of age, and then I'm attaching a purchase probability to each person that depends on their age. So this will ensure that younger people are actually less likely to buy stuff than older people. I have no idea if that's true in the real world, but this is all for the sake of illustration. And basically, we'll then spin a dice and see if that's less than the purchase probability. If so, then we'll say that that person bought something. Okay? So let's run this little bit of code. If you want to stop and study how that works, just to brush up your Python skills, feel free. But at a high level, that's what it's doing. Generating 100,000 random people, assigning them to a different age, and creating a number of purchases per person where older people buy more than younger people. So let's kick that off. And we can double check the results here by dumping out the totals broken down by age group. And sure enough, you can see that the age groups are pretty evenly distributed as they should be. So we have about the same number of 20-year-olds as 70-year-olds. Real world, that probably wouldn't happen, but whatever, we'll go with it. And now let's look at the purchases and make sure that there really is that dependence that we were talking about. So sure enough, 20-year-olds are buying a lot less stuff than 70-year-olds in this example. So we can say there is a dependence between purchases and age here, and conditional probability can help us tease that out. So let's start messing with conditional probability. First thing we're going to do is compute P of E given F, okay? And I'm throwing out new letters here just to confuse you. You kind of have to, that is the hard part with conditional probability, just wrapping your head around the notation. So in this example, we're going to say E means purchasing something, and F means you're in your 30s. So the probability of purchasing something given that you're in your 30s would be what? Now we could go back to that fancy equation that we had in the slides, but you don't always have to use fancy equations. Sometimes the data that you need is right in front of you. So a lot of data science is just kind of figuring out the simplest way to compute the value that you need. Given that I have the number of purchases that 30-year-olds have made, and I have the number of people that are in their 30s handy as well, I can just compute that directly. So all I need to do is divide the total number of 30-year-old purchases that were made over the total number of 30-year-olds, and I get the probability of E given F. Okay, and that works out to be about 0.3, about 30%. We could also work out the probability of F, which is the probability of being 30 overall in this entire data set. And again, we can compute that directly just by taking the total number of 30-year-olds divided by the total population size, which is 100,000. So the probability of being in your 30s, or P of F, is about 17%. Okay, let's actually execute these just to make sure that I'm not lying to you. Okay, and we can compute the P of E, where P of E is the overall probability of buying something regardless of your age. And again, we can compute that directly just by taking the total number of purchases that were made in our data set divided by the total population of people, and that works out to be about 45%. Okay, so if E and F were independent, if there was no relationship between your age and how much stuff you buy, we would expect P of E given F to be about the same as P of E. But we've computed both of those values, so we can compare those two together. So P of E worked out to be about 45%, but P of E given F was 30% roughly, if you go back up here. So given that those numbers are so different, it tells us that there probably is some dependence in there, and it makes sense to think about conditional probability. So next, let's compute P of E times P of F. And that is just, well, what it sounds like, the probability of being in your 30s times the probability of purchasing something overall, PE times PF, and that works out to be about 7.5%. Now, P of E comma F is different than P of E bar F. So PEF, remember, is the overall probability of being in your 30s and purchasing something, and P of E bar F is the conditional probability. So let's figure out P of E comma F. That works out to just be the probability of being in your 30s and purchasing something, which is the total number of purchases made by 30-year-olds divided by 100,000, so we can compute that directly, and end up with about 5%. Now, normally we can say that P of E comma F is equal to P of E times P of F, but that only works if those two things are independent of each other. So again, the fact that there is a dependency between E and F is throwing off some of our assumptions. And sure enough, 5% is not the same as 7.5%. So this rule that you might see elsewhere of P of E comma F equaling P of E times P of F, that's only true if there's an independent relationship. But because they're dependent on each other, they're not actually the same thing. So that's an important point to keep in mind. However, we can check that our original equation still holds. That does take conditional probability into account. So remember, back from the slides, we saw that P of E given F is equal to P of E and F together divided by P of F. And sure enough, if we do that math, it all works out. We end up with a 0.299, about 30%. And that does jibe with our original result back up here of about 30% when we computed that directly. So sure enough, our equation works. All right, whew, that's a lot of notation there to wrap your head around. But again, that is the hardest part of conditional probability. Concepts aren't that hard. So your assignment, a little bit of a hands-on experience here to get your feet wet. It's probably an important thing to actually immerse yourself in here and actually work with it hands-on. Now, I want you to go back to the code and change the original distribution such that the purchase probability does not vary with age, so that E and F are actually independent of each other. And run through these same equations and see how things work out differently. You'll probably see that, for example, P of E comma F does equal P of E times P of F, for example. And you might see that the conditional probability is no different than the probability without that condition. So go and make sure that's true. And if you think about why you're getting the results that you're seeing and why they're different than when there was that dependency, I think that will really help the concepts of conditional probability sink in. So go do your homework, and I'll see you in the next lecture. So there you have some examples of using conditional probability. Again, the concept's not that hard. It's just really easy to get tripped up on all the notation with all the pipes and commas meaning different things and stuff. But once you get used to it, it's not so bad. So I hope you have a chance to dive into the homework assignment here and try this little exercise of playing with it yourself and removing that condition and confirming that conditional probability ends up wiping itself out in that case. Let me show you my solution in the next lecture.